Hello, this is Mike Lively from Northern Kentucky University, and this is the third in a series of seminars at NKU, which are free to the public on Papervision3D and CS4. If you're joining us from YouTube, you can get all this information from my blog site, which is professionalpapervision.wordpress.com. And in this seminar today, we're going to discuss pendulums in 3D, and there's 4 pendulums we're actually going to look at. We're going to look at a simple pendulum, a double pendulum, a torsion pendulum, and a Foucault pendulum. And in each case, we actually expand upon the coding concepts. In the simple pendulum case, we'll look at basically encapsulation. The double pendulum, we'll look at pinning. The torsion pendulum, we'll talk about sliders. And the Foucault pendulum, we'll talk about environmental maps, making that look more realistic like a real pendulum. So let's get started with the simple pendulum. Now in the simple pendulum case, we want to deal with encapsulation, and the guy that does a really good job of that is Dehash. So just go to his blog, www.dehash.com, and he has a number of examples that you can visit. We actually looked at his double plane example and extended that example actually so we could actually control the plane. So he has an example of a double plane that stick together, you spin around, you could have a different image on each side. What we did, we actually just put a parameter in there through encapsulation and allowed those planes to bang up against each other. Let's check out that demonstration. So here we go. Let me catch that real quick. So you can see these two planes are spinning around and they're banging against each other with an oscillation as they spin. And Dehash didn't do that. We actually extended his code to make that happen. But he did use encapsulation with the other model that we'll use for the rest of this series. So what is encapsulation anyway? Basically, encapsulation, what we do is we have a main class and a subclass. And the main class is going to handle the basic view, that's the Papervision stuff, length, pinning, and animation. Where the subclass is basically just the elements, like the clothes, or the garments, or the pieces that are to be instantiated and animated and pinned. That's really all there is to it. But what having that subclass does for us, enables us to, in a sense, instantiate that over and over again. The super huge advantage here is that the pendulum elements can be substantiated and pinned as often as needed and used by any number of different programs. So it's extremely powerful techniques, and basically we just feed the animation right to the subclass. All you have to do is create a subclass, hit the imports, make sure your statements are public that you want to control, and call those up in your main class, and that's all discussed in the book. So let me show you the single pendulum. Let's click on the application. And there it is oscillating. I'm actually going to get a different line here, so let me reinitialize it. There we go, we got a different color. And there's a pendulum oscillating back and forth, and you can see you have a control over here. And this is the pendulum equation. And it's pretty much just based upon string tension versus gravity. And it's nonlinear, it's a sine theta, and you have to actually use numerical analysis to solve this correctly. In this case, we use the linear approximation. The neat thing about this, if you change the length, it gets longer until your pendulum gets longer. And you make it smaller, and your pendulum gets smaller. Let's do that. So you have a little slider here that's when you change this, your pendulum changes as well, which is kind of fun and very easily done in Flex. Let's go ahead and take a look at this real quick. And you can change a few more if you want. Longer or smaller. So by changing the length, you change the frequency. The oscillating frequency increases with smaller length, which is, of course, the inverse of the square root. So let's move on. So our next object is a double pendulum, and to create it you have to pin one object to another. Pretty cool. And the way that happens is in your subclass you have a pinning function. And all you do is do trigonometry. You just take the length of your segment, you multiply it by sine or cosine, add the present x and y to it, or subtract, and that gives you the xy position. So in order to pin, all you have to do is take the x position of your second pendulum and add to it the pin value of the first one, and the y position of your second pendulum, and add the pin value of the y one. And you can actually do this for multiple objects and create kind of a snaking scenario, and we'll do that in further post. So now I'll demonstrate the double pendulum. Let's click on that. And it's just basically two balls oscillating. Now what I've done, I've actually over-exaggerated the second angle, so when you get to the side it keeps oscillating out a little bit. That wouldn't be the case. It's actually a normal mode where both follow each other. Now that's one mode of a linear approximated double pendulum. Now, actually, if you want to solve this correctly, you need to use some numerical analysis like Runge-Kutta. And Keith Peters, in his book, actually has the source for Runge-Kutta. I've actually put it in the source files. And there's also an example in the blog. Just click on it, and you can actually see a bouncing ball. We'll move on to the next pendulum.